damp would simply not burn. If there was too little fire damp, the flame of a taper was merely enlarged in the mixture. And here we see a modern flame lamp. I ought to explain in advance that the gauze of the flame lamp is behind this bonnet here. This is a later development from the original Davy conception, whereby the whole of the lamp was constructed from gauze. But the main purpose in showing you this slide at this stage is to show you that in small concentrations of fire damp, the flame of the lamp is enlarged, as Davy himself had noticed. And in that phase of his work, what Davy had done was to establish the existence of what are now known as the flammability limits of a gas. And these limits define the range of concentration within which self-sustained combustion is possible. Moving on, he then found that the fire damp was not easy to ignite. It was not exploded or fired by red-hot charcoal or red-hot iron. And this property of difficulty of ignition forms the basis of intrinsically safe electrical apparatus, which is widely used nowadays, and is so designed that the sparking produced at any break of the circuit is intrinsically unlikely to ignite a specified flammable gas. And I will say more about that later on. Davy was then beginning to get to the heart of the matter. He investigated how flames were transmitted in various circumstances. He first experimented with flames transmitted through tubes, and he found that if the tubes were small enough and short enough, a flame would not pass, I should say long enough, a flame would not pass through the tube. Furthermore, metallic tubes prevented flame transmission better than glass tubes. And Davy summed it up in this way. In reasoning upon these various phenomena, it occurred to me that the effect of the surfaces of small tubes in preventing explosion depended upon their cooling power, upon their lowering the temperature of the exploding mixture so much that it was no longer sufficient for its continued inflammation. And this is the phenomenon that we now know as flame quenching. And Davy's observations provide the basis for many applications in which a flame is extinguished by careful design of the passageways along which the flame must travel. And examples are the flame-proof electrical apparatus and flame arresters that now find essential application in oil refineries, offshore platforms, and in the petrol pumps in every filling station. And again, I will come back to that as well. Davy then experimented with many systems of tubes and concluded that they were not effective. In rejecting them, he stated, and at last I arrived at the conclusion that a metallic tissue offered a perfect barrier to explosion from the force being divided between and the heat communicated to an immense number of surfaces. He thus arrived at the solution of surrounding the flame entirely by wire gauze. We will now illustrate for you what Davy had just found. Jeff is placing a wire gauze on top of a Bunsen burner which is being fed with butane, and you will see that the flame does penetrate the gauze rather quickly. And this is in line with an observation of Davy himself. The other Bunsen burner is fed with tar and gas, or largely methane, and if it behaves itself, the flame should not penetrate that gauze, even though the gauze has been previously heated by the other flame. So this had an important, or has an important lesson in that Davy himself realised that if he wanted to make a flame lamp that would be safe in a mine, he needed to ensure that it was able to prevent the transmission of any gases that were likely to be encountered in mines. And so he did all his development with coal gas. And coal gas transmits flame. It is easier to transmit through gauze than methane because it contains other hydrocarbons and hydrogen. And hence, if he could make a lamp that was safe in coal gas, it would be even safer in fire damp. So he was incorporating the factor of safety into his development. And the solution of surrounding the flame entirely by wire gauze was then the practical outcome of all this experimentation by Davy. And he observed that in plunging such a lamp into an explosive mixture, the whole cylinder becomes quietly and gradually filled with flame, the upper part soon appearing red hot, yet no explosion is produced. Now, I have a film which shows a flame lamp behaving in that way, and I remind you that the gauze of a modern flame lamp is contained in the upper part of the lamp. The lower part is the glass cylinder through which the light is transmitted. So this film, which was taken in a recirculating rig in which gas, in this case methane, and coal dust could be circulated past the flame lamp at high velocity. You will see that in the first test that is illustrated here, the flame of the lamp is filling the lower part of the flame lamp. Eventually, the flame will take up into the higher part where the gauze is, and you will see the gauze become red hot in precisely the way that Davy had observed. And very soon, as you now know, the external atmosphere of methane will be ignited. This second shot shows that the heating can become very intense, indeed almost white hot, and the situation can continue for a very long time before the external atmosphere is ignited. You may wonder why I have, in 1995, a film of this kind available. Why should anybody be doing experiments with flame lamps? It happened that there was an explosion at a mine in Australia in which a flame lamp was the suspected source of ignition in rather unusual circumstances, where a very high velocity of air with methane and coal dust would have blown past flame lamps and were suspected to have resulted in the ignition of the atmosphere causing an explosion, as happens here. There. So those observations on flame lamps were precisely as Davy had himself observed so many years ago. The wire gauze lamp that Davy invented was tested underground in January 1816, successfully tested and immediately adopted, and immediately Davy began to get very appreciative letters from miners, some of which you can see in the library. And I have, from our archives, extracted some slides just to show you the flame lamp being used as a source of light up until comparatively recent times. Not too recent, because you notice that this particular miner is not wearing a safety helmet, so it was probably sometime before the war. And that miner is, in fact, setting explosives in the coal face prior to the shot firer here, bringing the or exploding the charge and bringing the coal down. So again, you can see the two flame lamps being used as the only source of light in that situation. Now, although he had many other things to do, Davy didn't rest on his laurels as soon as the lamp was proved to be successful. He realized that the flammability limits, which I've mentioned earlier, depend on the temperature. And so he regarded it as important that he should study the effect of the preheating of the fire dampened air due to the heating up by the red-hot gauze. You can just visualize the circumstances of the fire damp air mixture entering the lamp through that red-hot gauze, raising the flammability limit, and he was interested in the effect that would have. As a result, and I quote, he undertook experiments on the nature of flame and the modifications of combustion that led me in January 1817 to an important practical addition founded on an entirely new principle. And what he then described was his accidental discovery of catalytic oxidation. And Bryson will be demonstrating as I go along. In his experiments, Davy introduced a small wire gauze safety lamp with some fine platinum wire fixed above the flame. He introduced this into a mixture of fire dampened air at the upper flammability limit. And when the flame took hold in the wire gauze cylinder, as you saw in the film, he introduced more gas, expecting the flame to be extinguished unless the heating of the gas by the wire gauze prevented it. He noticed that the flame continued for only 2 or 3 seconds and was then extinguished. But more important, he noticed a curious phenomenon. The platinum wire continued to glow, even though there was no flame in the cylinder. It was immediately obvious that the oxygen and gas in contact with the hot platinum were reacting without flame and producing enough heat to keep the wire glowing, as you will see here. He proved this by making a similar mixture, heating a fine wire of platinum and introducing it into the mixture as Bryson has just done. Except that Bryson uses a platinum foil and the liquid that is in the flask is methanol. And Davy found that if the wire was repeatedly taken out, and Bryson will reproduce this effect, and allowed to cool in the atmosphere until it ceased to be visibly red, and then reintroduced, it instantly becomes red hot. And Davy repeated the experiments with other flammable gases and vapors. So Davy found it with fire damp, and Bryson has just found it with methanol. Davy tried to produce the phenomenon with various other metals, but succeeded only with platinum and palladium. He surmised, wrongly as it happens, that the explanation lay in the low thermal conductivity and small heat capacity of platinum and palladium compared to other metals. The catalytic oxidation is a much more complicated phenomenon. Davy predicted that many theoretical views would arise from the connection of his observed facts respecting slow combustion, and hints for new researches which he hoped to be able to pursue. And of course that has come to happen. He described the practical application. Remember, he was still working on the minor safety lamp. He described the practical application of his discovery thus. By hanging some coils of fine platinum wire above the wick of his lamp in the wire gauze cylinder, the miner will be supplied with light in mixtures of fire damp no longer explosive. And should his flame be extinguished by the quantity of fire damp, the glow of the metal will continue to guide him, and by placing the lamp in different parts of the gallery, the relative brightness of the wire will show the state of the atmosphere in those parts. Now, this part of Davy's work on catalytic oxidation and on the development of the safety lamp has a direct connection with modern gas detection instruments using the Pellister. The Pellister is a device which relies on the catalytic oxidation of fire lamp by palladium. It's a miniature transducer in which a flammable gas is oxidized on a small ceramic bead coated with a palladium catalyst and heated by a coil of platinum wire embedded in it. And there is a model of this in the library as part of the exhibition. And the heat of oxidation raises the temperature of the bead, and the temperature rise is indicative of the concentration of the flammable gas. The Pellister has since become the basis for the standard handheld instrument used by the supervisory staff in mines, as well as for extensive automatic detection systems monitored from the surface control room. And it finally brought to practical fruition, in aid of the miner, the application of the entirely new principle first observed by Davy and his researchers on the safety lamp. And there is a certain beautiful symmetry about those two developments. Aside from safety, catalytic oxidation has many other applications, perhaps the best known being the catalytic converters that are now required to be fitted to motor car exhaust systems to reduce atmospheric pollution. Platinum catalysts are now widely used in industrial processes, with applications ranging from the production of nitric acid needed for fertilizers, explosives, and synthetic fibers. And I have an example just to illustrate that. Here, a packet of Sainsbury's nylon tights. So there's a connection between Sainsbury's nylon tights and Davy's safety lamp.